Hmm. Okay, good morning, everyone. Okay, we are considering the invertibility, and this is quite important. So let me go over again one more time briefly, and then we go to the next slide section. So suppose that we have a linear mapping T from V to W, and U is a mapping from W to V. And this U is special in the sense that when we consider the composite of T and U or U and T, you get the identity mapping. If such U exists, then we say T is invertible. And at that point, the U is called an inverse. We can easily show that this inverse, if it exists, it must be unique. And symbolically, we use this t to the negative 1 to express this inverse. Okay, so that is the definition of the inverse of any linear function. If t and u are invertible, then then tu, the composite of two invertible functions, will be also invertible. And in addition, its inverse can be easily found. What you need to do is, okay, given t, the composite of t and u, the inverse will be the composite of u inverse and t inverse. You need to change the order. I mean, the order is the you need to take the reverse order of this operation. And if t is invertible, then t inverse will be also invertible, and the inverse of t inverse will be the t itself. So this slide shows the definition of an inverse or invertible mapping for any linear transformation. And we learned that in other courses that if your mapping is invertible if and only if the map and actually the mapping is one to one and onto. Okay, and dimension. So okay, one to one and onto. Now theorem 2.5 shows the equivalence of these three statements. In other words, if your linear transformation is invertible, then this t must be one to one and onto, so that the dimension of the domain and dimension of the range and rank of this t, they all must be the same. So the invertible t is invertible if and only if the rank of t equals the dimension of the domain. And what we proved, I guess we proved that the dimension of the codomain also equals this rank if your mapping is invertible. That's what you can derive. And in example 1, we considered a linear mapping T which maps a plus bx to this pair of numbers. And then the example gave you this mapping, certain linear mapping which maps a pair of numbers c and d to this first order polynomial. Then you can show that this mapping from c and d to c plus d minus cx, that mapping will be the inverse of the original mapping T. You can check it yourself. And the theorem 2.17, that okay, the third theorem considered this shows that if T is linear and invertible, if T is linear and invertible, and then, as I said, the T inverse is also invertible, and it must be linear. So if T is linear and invertible, then T inverse will be linear and, of course, invertible. We can consider this as a proof. I mean, we can consider this proof, right, given this slide, right? And we will consider another viewpoint in a second. And as I said, if T is an invertible linear transformation from V to W, then V is finite dimensional if and only if W is finite dimensional, and in addition, their dimensions must be the same. So as I said, the dimension of the domain, rank, dimension of the codomain, they all must be the same if your linear transformation is invertible. Now, so those were some explanations for general linear transformations. Now, this slide considers the invertibility of a matrix. Given some n by m matrix, your matrix A is said to be invertible if there exists a certain B matrix such that A times B and B times of A both produce identity matrix. Okay? Then we say A is invertible and this B is called an inverse, and this inverse will be unique. The uniqueness comes from here, and A must be an n by n square matrix in order to have this relation here, I mean this condition, because in order to consider the product of A and B, the number of columns in A must match the number of rows in B. And if I think of B times A, then number of columns of B must be the same as the number of rows in A matrix. So in order to define AB equals BA equals I, A and B must be n by n square matrices. Otherwise, we cannot derive with this. So this is the definition of the invertibility. Okay, invertibility requires this. Okay, but later I will eliminate one of these. But anyway, so invertibility means A time. So we must have an inverse B satisfying this equation, this relation here. And when you multiply these two, you get the identity matrix. So one is the inverse of the other. Now, this theorem, 2.18 says, if V and W are some general vector spaces with some basis, and T is a linear mapping from V to W. Now, if I have these bases, then we can always derive one and only one matrix representing this linear transformation. Okay, that's what we learned previously. Now the theorem 18 says, if your T is invertible, okay, as a linear transformation, if it is invertible, then its matrix representation must be invertible as well. And if this matrix is invertible, then your T is invertible. And in addition, the the matrix representing this inverse of the linear transformation, that will be the inverse of the matrix representing T. And the basic theorem was a 2.11 that was quite useful in many proof. So 2.11 says if I have two linear transformations T and U, and with some appropriate basis, we could find these two matrices, then the product of these two is the matrix representing this composite. So that is the claim, that is the conclusion from theorem 11, and this the theorem 11 is used quite often to prove certain identity or to prove a certain formula. So in theorem 2.18, to prove this idea, we first assume that so this linear transformation is invertible, so that this invertibility of T means there will be some operator, certain mapping U, right? Such that T, the composite of T and U is the identity mapping. And in that case, that U is denoted by T inverse, this notation. So in other words, the composite of T and T inverse will produce the identity mapping. Okay. And identity mapping is the matrix. Identity mapping has identity mapping has identity matrix as its representation. So identity matrix is the representation of this identity mapping, and if I use this theorem 2.11, I can split this matrix as a product of these two. So when I multiply these two, you get the identity matrix. That means one is the inverse of the other. So that's why we derived this. And actually, all these arguments are reversible. So if I assume that your matrix, certain A matrix representing this linear transformation is invertible, then this invertibility implies the existence of some B satisfying this. Then from this B, we can introduce certain U matrix, U mapping, such that, such that, such that, okay, so this is correct, I mean, the true. Now, such that when you have this product of these two matrices representing U and T, eventually that is the same as the matrix representing the composite. And here I'm using this theorem 11 one more time. Okay, so if A is an invertible matrix, then we can find the inverse matrix, and from this inverse matrix we can construct U which behaves as the inverse of the original mapping. So the composite of T and U will be the identity mapping. So T is invertible. Okay? So this is important. So if T is invertible, if T is invertible, then the matrix representing T will be also invertible. Okay, but the invertible, but I mean, so if T is invertible as a linear mapping, then its matrix version, matrix representation will be invertible as a matrix. Okay, and the inverse of linear transformation has certain matrix representation, right? And that matrix representation will be the inverse of the matrix representing the original T mapping, which is this. Moments ago, I considered example 1, which considers this T and T inverse. Okay? And if we construct, okay, the matrix representation for T and T inverse, and if we use the standard ordered basis, then the matrix representing T will be this, and the matrix representing T inverse, this one, will be this matrix. When you multiply these two, you get the identity matrix. That means one is the inverse of the other. Okay, then let me go back to this one more time. So in theorem 2.18, I have this conclusion here. So later, we will study, okay, we will study how to find the inverse of a matrix. Okay, so given A, we will study how to find the inverse of a matrix. Now, if I know that trick, then if I know the trick, then I can easily identify the matrix representing the inverse operation, right? By this. So given this A matrix, if I learn how to find the inverse of A matrix, then that will be the matrix representation of T inverse. So given beta and gamma, I can easily construct T inverse transformation. Okay? So that's how we are going to construct the T inverse in general. So in general, it is very challenging to, so given T, it is difficult to find T inverse mapping. I mean, we can do that, we can find, but finding T inverse from T, this one is a little bit difficult. Okay? So what we are going to do later in the future is, given A, we are going to find the matrix version, matrix representation of T. Okay? And that is simple as long as you have some basis, right? Given A, we will study how to find the inverse of A matrix. We will study the trick soon. Once I have this, and since the bases are given, I can construct a T inverse. So this approach will be simpler than finding T inverse directly from T in general. But sometimes finding T inverse directly may be simple enough, but in general, finding A and A inverse and then finding T inverse from A inverse will be much easier. Okay, well, yeah, you can. This is a simple enough. You can read this. Okay, now, given two vector spaces V and W, we say V is isomorphic to W if there exists a linear transformation T from V to W that is invertible. Then, as I said, if T is invertible, then the dimension of a V and dimension of a W will be, if they are finite dimensional, then the dimension of a V and dimension of a W will be identical, will be the same, right? Anyway, so if such invertible T exists between V and W, then we say V is isomorphic to W. And that specific invertible transformation T, that will be called an isomorphism. So isomorphism is an invertible linear transformation. Okay? So a linear transformation, a linear such, meaning a linear invertible transformation will be called an isomorphism from V onto W. So if I define T from F2 to P1 by this, then this is definitely an invertible mapping, invertible linear transformation. So this T is an isomorphism, and we say the domain F2 space is isomorphic to P1 space. Isomorphic. So that means when you observe certain events in F2 space, you will find a similar observation in P1 space, and vice versa. In example 5, let us consider the mapping T from P3, the polynomials of degree 3 or less. Okay, and M sub 2 by 2, that is a 2 by 2 matrices with real entries. And here T is a mapping which maps any polynomial in P3 space to this 2 by 2 matrix. Then you can show that this is linear mapping. Now, I said an invertible linear mapping is an isomorphism. And if this T is an isomorphism, then P3 space and M sub 2 by 2 will be isomorphic. So to claim that these two spaces are isomorphic, I need to show that this T is an invertible mapping. Or you need to find the inverse directly. But instead of finding the inverse directly, we can consider the following statements. First of all, definitely this T is a linear mapping. We can easily check. And P sub 3 is, what is the dimension of this? 4. That is the dimension of M sub 2 by 2 space. So dimensions are the same. And is it one-to-one? Yes. How can I prove it? When you consider the image of this mapping, and if the image of the mapping is set to 0, so if I assume that this is a 0, meaning you have a function something like this is given. This is a cubic polynomial at best, right? I mean, depending on these coefficients, this f of x may be a second order or first order polynomial, but in general, okay, this may be a cubic polynomial. And even cubic polynomial, if the shape of the cubic polynomial will be this or this, meaning the number of intersections with the x-axis will be at most 3. If I assume that the image of this mapping is 0, then that means f1 is 0, f2 is 0, f3 is 0, f4 is 0. That means my function f goes through the x-axis at 4 points, not 3. That happens only when your f is identically 0 function. So if I consider this zero mapping, I mean the zero image, that zero image is obtained only when the vector in the domain is the zero polynomial. Otherwise, you have a cubic polynomial, and as I said, in that case, the number of zeros will be at most 3 or less. So if you have 4 different solutions, then your function must be the zero function. So if I assume that the image of a certain polynomial is 0, then that implies that f is identically 0. So you have 0 norm space and the mapping will be 1 to 1. Since the mapping is 1 to 1 and the domain and codomain have the same dimensions, okay, then your mapping will be onto and the rank of the mapping will be the same as the dimension of the domain and so on, right? So anyway, so dimensions are the same, dimension of these two spaces are the same, and the mapping is 1 to 1. So we can derive that the mapping is onto and the rank and the dimension of the domain P3 are the same. And if the mapping is 1 to 1 and onto, and if the dimension of the domain and codomain are all the same, then the mapping will be invertible. So we don't have to construct the inverse mapping, but we could verify that this mapping is invertible. So this mapping T is an isomorphism, and P3 and M sub 2 by 2 will be isomorphic. So in example 5, as I said, we didn't find the inverse. We didn't find the inverse of T directly, but we could confirm that this T must be an invertible linear transformation. That's why T is isomorphism and P3 is isomorphic to the M sub 2 by 2. Now, theorem 2.19, if V and W are finite dimensional vector spaces, and if V is isomorphic to W, then these two spaces, V and W, must have the same dimensions. This will be trivial, right? If they have different dimensions, then it cannot be 1 to 1 or it cannot be onto. One of these two properties cannot be satisfied. But anyway, let's check this proof briefly. So suppose that V is isomorphic to W, so that we have some isomorphism from V to W. Well, if this is an isomorphism which is invertible mapping, then the domain and codomain must have be the same. And if dimension of V and if the dimension of W are the same, and if we consider two bases, beta and gamma for the domain and codomain, then we can always find a linear mapping T which maps Vi to Wi, right? And this mapping must be unique. Please remember that we have a unique mapping T which a T such that T is a linear and T maps each Vi to Wi. And since Vi's are the basis, the range is spanned by the images of these Vi's. So the range is generated by the images of the vectors in the beta. Okay, and since T is a mapping which maps Vi to Wi, the images of the vectors in beta will be just the basis gamma. Okay, and what is the gamma? Gamma is a basis for W, so its span is W. So the range and W, the codomain, are the same. So the mapping will be onto. Then that's it, right? Since the dimension of V and dimension of W are the same, and if the mapping is onto, then the mapping must be automatically one-to-one, so that it will be definitely invertible. Since T is invertible, your T is an isomorphism. Okay, you can read this, which is simple. Now, in theorem 20, suppose that V and W are finite dimensional vector spaces over the same scalar field F, but suppose that V and W have possibly different dimensions, say n and m. The domain is an n-dimensional space, and W codomain is an m-dimensional space. And let me consider two bases, beta and gamma, for the domain and codomain. Then, please remember, what is this? L of V and W. That is a vector space. That is the collection of all the linear mappings from V to W. Okay? So that is this collection. And M sub M by N is the collection of all the M by M matrices. And I want to consider a mapping phi which maps linear transformation T from V to W to its matrix representation. Please remember that for any linear transformation, we can always find its matrix representation if some bases are given, and that matrix representation is uniquely determined once this beta and gamma are given. So the mapping from T to its matrix representation is well defined. Okay, so this phi, this mapping phi is well defined. This is a well defined mapping from L of V and W to M sub M by N. Okay, this is a well defined mapping, and that will be linear. You can think of it. And is it 1 to 1? Yes, because the matrix is uniquely determined. Is it onto? Yes. Now, what do you mean by onto? Onto means if I choose any vector from the codomain that belongs to the range, and you can think of any matrix in this space, then I can construct a linear transformation having that matrix as its own representation. Do you understand this? So you can read the okay. Okay. So I'm just saying this phi mapping phi is an isomorphism. What is the definition of an isomorphism? It is an invertible linear transformation. So to prove that this T is an isomorphism, I need to show that this mapping is, first of all, well defined. It must be a function. It must be a transformation, right? So, but that is well defined. You can, so what I'm saying is it is well defined that it is a must, right? Second, it is a definitely a linear mapping. You can check again. Third, it is 1 to 1 because I told you that if I have any linear mapping and once bases are given, you have only one and only one matrix representation. So the mapping is 1 to 1. So these three are quite simple. Number four, it must be onto. That means onto means codomain. Codomain is the same as the range. That means if you choose any matrix from the codomain himself m by n. So if you choose any matrix, that is a matrix representation of some T transformation. So this portion just identifies this sum part. Okay, so that is simple. So you can read it. So by this, so you have a well-defined linear 1 to 1 onto mapping. So this 1 to 1 and onto implies that your mapping is invertible. So so T this phi is an isomorphism. Phi, not T. Okay. So the the subject of the sentence is phi is an isomorphism, not T. And that means these two spaces are ortho isomorphic. Suppose that V and W are, V is an n-dimensional space and W is an m-dimensional space. And sometimes many students get confused with the dimension of this space. Okay. But dimension of this space is m times n, And we can even construct a basis, right? I mean, so if I have just one in the ith row, jth column, and all the other entries are 0, so if I call this guy as B sub ij B to the ij matrix, then this will be a basis. This is a basis for M sub M by N space. So the dimension is M times N. So that is the dimension of this space. Okay. So this is one usage of this isomorphism. Okay. Suppose that beta is an ordered basis for n-dimensional vector space V over certain scalar field F. Then the standard representation of V with respect to beta is the function phi sub beta which maps x to this coordinate. So that's the standard representation of V with respect to beta. Okay? So x vector is mapped to its coordinate. As an example, when beta is given, the standard basis in R2 space, then any vector x, say 1 and -2, that phi sub beta maps x to its coordinate, which is 1, -2. So in this case, yeah, so this is the image of x. But if I use the gamma as a basis, 1 and -2 is -5 times 1 and 2 plus 2 times 3 and 4. Okay. So phi sub gamma maps x to -5 and 2 vector. Okay. So please be careful when I say the standard representation of V, and then if I give you a specific basis beta, then this mapping maps x to its coordinate with respect to beta. So this is the coordinate of x with respect to beta. So mapping sending x to its coordinate will be called standard representation of V. And these are two examples. Then, for any finite dimensional vector space V with ordered basis, this mapping is linear and one-to-one and onto, so that it is an isomorphism. Okay, right? So please let me let me go back to this definition. The standard definition, phi sub beta maps any vector to its coordinate. So if I consider, say, phi sub beta is trivial, so let me consider phi sub gamma. Okay, then x is mapped to -5 and 2. Okay, and if I consider, say, y vector, and let me consider, say, 1 and 2 vector, so that is 1 times 1 and 2 plus 0 times 3 and 4, so that the coordinate of y with respect to gamma is 1 and 0. Then phi sub gamma of x plus y will be phi, phi sub gamma of, if I add 1 and 2 to this, you get 2 and 0. Okay, then that is -4 times 1 and 1 and 2 plus 2 and 3 and 4. Okay, then, right, so you get the linearity. I mean, I'm just showing an example. This is not a proof, but this example shows certain linearity will be satisfied. And how about the one-to-one? If phi sub gamma maps a certain vector to 0, then that means 0 means, what does that mean? Then this 0 is the coordinate of z with respect to gamma. What does the coordinate imply? Z can be constructed as a linear combination of the bases in gamma using these numbers as coefficients. But since these two numbers are just zeros, z will be 0 and 0 vector. In other words, z is 0. So the mapping is 1-to-1. Then is it onto? Yes. How can I show it? Please remember this phi sub gamma is a mapping from F2 to F2 in this example, right? Now, in order for this phi sub gamma to be an invertible, the onto mapping, the range and codomain are the same. If you choose any pair of numbers from the codomain, F2 or R2 in this case, we can always find a vector in the domain. I mean, for any pair, say AB in F2 space, F2 space, this AB is the coordinate of certain z vector, right? For some z. Why? Because because I can literally construct z. A times 1 and 2 plus B times 3 and 4. And if I call this guy as a z, this one. So that means the mapping is, so the mapping is onto. Because when I choose any pair in the, for any pair in the domain, I mean codomain, it is an image of something. Image of something here. So it is, so this part shows that this mapping is 1-to-1. and this upper portion shows that the mapping is onto, so it will be invertible, right? And the mapping phi sub gamma will be an isomorphism. And the trick I'm showing you can be generalized into any space. So if you write down this properly, we can show that this phi sub beta is an isomorphism, meaning it is a linear one-to-one and onto. So that the mapping is invertible. So let V and W be a linear transformation, and if given some basis beta and gamma, so beta is a basis for V and gamma is a basis for W. And as I said, suppose that we have a linear transformation T from V to W. So if I want to find the image of a certain vector, you can directly apply the definition T. Or since I have beta, for any vector I can find its coordinate, then I can consider its and then I can find a matrix A representing T. Okay, so here given any say V vector here, then x is the coordinate of V with respect to beta. L sub A maps this x to A times x. And the theorem says that this A times x is the coordinate of the image with respect to gamma. Then since gamma is given and phi sub gamma is invertible, I can construct T of V. Okay. Of course, in this diagram, this image, okay, this coordinate of the image with respect to gamma can be found this way or this way. So the left hand side is the calculation obtained from the first approach, and this second approach evaluates this part. And these two are the same. Okay. So in other words, if I consider the approach 1, then for any V in V space, you first apply this phi sub beta mapping, and then you need to apply L sub A transformation. In other words, you need to consider the composite of these two. But the second approach evaluates the image of V first, and then you consider this standard representation of W using this phi sub gamma. So that is the composite of phi sub gamma and T mapping. Okay, so as I said, this is a very important diagram. So from here, we get this result. And Yeah, in many fields, instead of applying the second approach, people considers the first approach. I mean, people sometimes prefer the left hand side expression other than the right hand side expression, even though the right hand side expression is more, straightforward, because we may have some benefits by considering the L sub A mapping. And we will see some examples. Okay, so let us consider the following example, which is quite interesting. Suppose that we have a linear transformation T from P3 to P2, and previously we considered the differentiation. Okay, and if I assume the standard ordered basis for P3 and P2, then the matrix representing this differentiation can be found by this. And since I explained this a few times, you are familiar with this matrix, I guess. Now, let us consider a particular polynomial. And suppose that I want to differentiate this polynomial. Okay? So, to differentiate this p, there are two ways. One, you can directly apply t to this p. Then, so if you know how to differentiate the polynomials, okay, then we can directly apply t. Okay, or so given this t from p3 to p2, so we have this p polynomial, and what is the coordinate of p, okay, with respect to beta? And if beta is the standard basis, then the coordinate of this p will be 2, -1, 2, 1, -3, and 5. So if I multiply this with a matrix A, you get this triple numbers, and that is the coordinate of the image with respect to gamma. So what does this imply? That T of P can be obtained by a linear combination of the bases in gamma. So gamma consists of 1, x, and x squared. If you multiply the first entry to 1 and the second entry to x and the third entry to x squared, and then if you add them, that will be the image of this mapping under T. Okay, so that will be the image of this image of P under T. So as I said, there are two ways. Okay, you can directly applying the differentiation, or we can consider the coordinate of the vector. This is the coordinate of P with respect to beta, and then you can multiply that coordinate with A to get the coordinate of the image with respect to gamma. Then you can just consider the linear combination of the vectors in gamma using those entries. So that's how we can use this standard representation or matrix representation of a linear transformation. So you need to practice how to derive a matrix once bases are given. So let me consider different example here. What if I change the basis? So if basis beta is the same, say 1x, x squared, and x cubed, but what if I consider different bases? Say gamma is consists of say x squared, x, and 1. I just reordered this. Then we need to find the corresponding A matrix, right? So how can I find A? You first map each vector in beta. So T of 1 is 0, T of x is 1, T of x squared is 2x, and T of x cubed is 3x squared. Then what is the coordinate of 0 with respect to gamma? Just the zeros. And to get 1, I need to multiply 1 to the constant 1 and 0 to x and x squared. So the matrix must be 0, 0, 1. And the image of x squared is 2x. So the coordinate of 2x with respect to gamma will be 0, 2, 0. And the coordinate of 3x squared will be 3, 0, 0. So this is my A when these two bases are considered. Then what is the coordinate of P with respect to beta? Since beta is still the same, you get 2, 1, minus 3, and 5. Now, if I multiply A with this coordinate, so if you multiply 0, 0, 3, 0, 0, 2, 0, 0, 1, 0, 0, and then 2, 1, negative 3, 5 is multiplied, then you get 15 and minus 6 and 1. So that is the coordinate of the image when nu gamma is used as the basis. So T of the P must be a linear combination of these three, x squared, x, and 1. So you put x squared, x, and 1, and then you multiply these three numbers, 15, negative 6, and 1, and then if you add them, you get 15x squared minus 6x plus 1. So that is the same as this image, but since the bases are changed, in this example, the matrix A is changed. Sometimes A and beta will be changed, okay, and but the result, the result of the multiplication will be the coordinate of the image when gamma is used as the basis. Okay, so then let's go to the next section. Um, okay, in many areas of mathematics, a change of a variable is used to simplify the appearance of some expression. For example, in calculus, an antiderivative of 2x e to the x squared can be found by making some simple change of a variable. So if I introduce a new variable u to represent x squared, then this e to the x squared can be simplified to e to the u, and 2x times dx will be du, right? I mean, if you are not certain when u is x squared, then du dx is the derivative of u with respect to x, which is 2x. And then if I multiply dx to this equation, then you get du will be 2x dx. So we get this. And so that means I'm integrating e to the u with respect to u, which is simply e to the u. And since u was defined by x squared, we get this. So that's what you studied in calculus class. So such change of a variable is quite common in mathematics, and it has many names. And similarly, if you consider some differential equation, sorry, not different, in geometry, if I given xy, okay, given some equations in x and y variable, when I introduce new variable x prime and y prime by this, then the equation becomes this. What does that mean? In terms of x and y, you have some ellipse in xy axis. But if I introduce a new variable, the equation can be quite simple. So, so this change of a variable appears quite often in several fields of mathematics. Okay, calculus, geometry, sometimes the differential equations, right? And if you came from engineering, probably the situation will be the same, right? And the change of a variable in linear algebra is equivalent to change of basis. Okay, so in this section, we want to consider the effect of introducing different bases. So people always stick to the standard basis. So when the P2 space is considered, people want to consider, say, a standard basis of 1x x squared. And if they consider the matrices M sub 2 by 2, then they just have four simple ones with many zeros and single one. So these are considered, but those bases may not be helpful in some situation. Okay, so in this section, we want to consider the effect of different bases. Okay, in theorem 2.22, suppose that beta and beta prime are two bases for the same space of V. Okay, and Q denotes the matrix representing the identity mapping, but I'm just changing the basis from beta prime to beta. Okay, first of all, how do I obtain this? How do I obtain this Q matrix? So before I consider this a general proof, suppose that beta is the standard basis, x1x in P1 space. Okay, and beta prime is, say, 1 minus x and 1 plus x. Then when I say the identity mapping, identity mapping in P1 space will map 1 to 1 and x to x. That's the what the identity matrix does. Then what is this matrix in this example? Well, this 1 is 1 half of 1 minus x plus 1 half of 1 plus x. And x is negative 1 half times 1 minus x plus 1 half of 1 plus x. So when I express this image of 1 as a linear combination of the vectors in beta prime, the coefficients are 1 half and 1 half. So the matrix has 1 half and 1 half in the first column. Then we consider the image of x. The image of x is x, but when I express this x as a linear combination of the vectors in gamma, then the coefficients are negative 1 half and 1 half. So negative 1 half and 1 half will fill the second column of this matrix. So that's the matrix. That's how we constructed this matrix. So even though we are looking at the identity mapping, the matrix is not can that matrix cannot may not be the identity matrix. Previously, when we consider the same basis, say when beta and beta prime are the same, even 1 minus x and 1 plus x, in that case, this identity mapping maps 1 minus x to 1 minus x and 1 plus x to 1 plus x, and 1 minus x is 1 times 1 minus x plus 0 times 1 plus x, and 1 plus x is 0 times 1 minus x plus 1 times 1 plus x. So this 1 0 go to the first column of the matrix, and this is 0 and 1 go to the next column. So when two bases are the same, then even though the basis is not the standard ordered basis, the matrix representing this identity mapping will be just identity matrix. So when beta and beta prime are the same, then the matrix representing the identity transformation will be always identity matrix, even though the beta is not the standard basis. But if two bases are different, as in the first example, then even though the mapping is identity, the matrix may not be the identity matrix. So if I go back to this theorem, so in this theorem 22, we are considering two bases, beta and beta prime. And Q is a matrix representing this identity mapping, but beta prime and beta are used. Okay. Then the first claim here is that Q will be still invertible. Okay. But this is a trivial because identity mapping is a invertible transformation. Yes. So Q, the corresponding matrix, must be invertible. That's what we considered. And for any V, this will be this. But this one follows the definition of the linear transformation. Please remember that when I have a mapping from V to V and I have T and we consider it the phi sub beta and A matrix and phi sub beta prime, phi sub beta prime and phi sub beta. Then, as I said, these two approaches are they have the same destination, right? In this theorem, this T is just the identity mapping. This is just a special case. So we can easily derive this fact. Okay? Okay, so let's call it a day here and see you next time. Okay, thank you for listening and have a nice weekend.